Okay, welcome to the last part of our linear algebra recap lecture. So what we wanted to discuss now, or what is the last missing thing here, is to define also norms on matrices. So we make the step now from these vector norms, which measure the length of a vector, to the matrix norms, which measure the length of a matrix. So what we can do is just do basically the same trick. We have applied a function element-wise on the vector elements, and now we do this element-wise on the matrix elements. But there's also another interesting way to define the norm of a matrix, and that is the operator norm, and it's denoted like this. It's then computing the maximum of all vectors which has a norm of 1, which has a length of 1, and then we measure the length of A times V. So this here is actually a vector, and this is a vector norm as we know it. So then there are different ways to define this. For example, this norm can be the 2 norm, and this norm can be the 1 norm, or something else. But we just keep it simple. So here we have in both cases the Euclidean norm, and the length of the vector V is equal to 1, which means that it's just an indicator of a direction. It's just important which angle it has, not which length. And then we apply the matrix product of A times V here, and then we try to find the direction in which the matrix product is actually increasing the most. So for vectors, we had also that the norm is actually related to the inner product of matrices. And then we also have looked about like special cases of the product, for example, orthogonality between vectors. And the same we also have with matrices. A matrix A with orthogonal columns defines actually the following equation. So A transpose A is equal to the diagonal where the length of each column vector is on the diagonal. So what you can do here as an exercise is to apply here the definition of the matrix product for A transpose times A, and then what is according to the definition by the inner product actually the outcome. And then you see that the outcome actually has to be a diagonal matrix. Now, if the columns are not only orthogonal to each other but also orthonormal, then we actually get the identity matrix if we multiply A transpose with A. And then we get the result that a square matrix, oh, this is X here, but this should be A, is called orthogonal if A transpose is equal to A transpose equal to the identity matrix. Okay, so this is the most important thing here, like the definition of an orthogonal matrix. And if you look at this definition here, what does it remind you to? Well, it's the same as for the definition of the inverse. So that means that A transpose is actually an inverse to A for an orthogonal matrix. Now, how does the norm and the orthogonal matrices rely actually to each other? A vector norm is called orthogonal invariant if for all vectors V and R to the power of n, and orthogonal matrices X, which are n times n dimensional, we have the following. So basically multiplying a vector with an orthogonal matrix does not change its length. And this is the case actually for most matrix norms. There is also an exercise in the accompanying math sheet where you can try to calculate this for yourself. It's not super difficult. Now, a matrix norm is called orthogonal invariant if basically the same holds only now for matrices V, which are n times d dimensional, and orthogonal matrices X, which are n times n dimensional. So again, the matrix norm of the matrix V does not change if we multiply with an orthogonal matrix. Now, the intuition behind this is that if we have the vector V and then we have X times V, then the length will be the same. But it might be rotated, so this might be then X times V. Okay, let's have a look at another important matrix operation, the trace. So the trace sums all the elements on the diagonal of a matrix. So if we have here an arbitrary matrix, so what the trace does, it just sums all the elements here on the diagonal. So it's 3 plus 1 plus 2. This is equal to 6. Now, very stupid definition in that sense, but has very important applications and implications. Yeah, what we look at here now is some rules to compute with the trace. So for example, it's linear. So that means if we multiply with the scalar c, and we have two matrices A plus B, then it's the same like we multiply with C and then compute the trace of A plus the trace of B. It's invariant under transposition of its arguments, so trace from A transpose is equal to trace from A. And it has the so-called cycling property, which is super nice if you want to calculate with it. So the trace from A times B times C times D is the same like the trace from B times C times D times A. And what I did here is I put the A at the end, so I cycle around. So the A is now at this position here at the end, and now I can again put the B up to the end, and then I get this term here. And then I can put the C up until the end, and then I get this term, and everything else stays the same here, right? Dub, and here is dub. Okay, so this is the cycling property. Now there is an important connection, for example, for the L2 norms and the trace of the product. For any vector V and a matrix A, so the definition of the 2 norm to the square is equal to V transpose times V. You can arrive to this conclusion from in multiple ways. So, for example, you could take the definition by the cosine of the angle between them, because the cosine of 0 is equal to 1. But you can also just go to the definition, which is summing up the element-wise multiplication of V. And this is then equal to the trace of V transpose times V. Now this is here not very interesting because the trace is just summing up the diagonal, and V transpose times V is here just a scalar, so one number, and the trace of that one number is then that one number, right? So this does not really change much. And here we have a similar relationship for the L2 norm of matrices to the square, which is then also the trace of A transpose times A. And this property is important because therewith we can derive something which is like the binomial formula, only for vectors and matrices. So you remember binomial formula, right? So it's like A plus B for some numbers to the square is equal to A squared plus 2AB plus B squared. And we can do this now with the norm. So the norm of x minus y to the square, yeah, this is then the inner product of x minus y transpose times x minus y. And if you calculate this according to the rules we have for inner product and the sum, so it's basically just distributivity. So we have x transpose times x minus x transpose times y minus y transpose times x plus y transpose times y, and then we can insert the definition of x transpose times x, which is the norm to the square of x, and the same for y. And then in the middle we have here the inner product of x and y. So I don't know if I think we have not defined it like this with these angles, right? But this is also a notation for the inner product. So here we have x transpose times y. And then you see like this is basically a similar shape like the binomial formula. And the same we can do with matrices here. So here we have the norm of x minus y, and then we insert here the definition according to the trace. And then we do again the same, like just apply the distributivity, and then we arrive at this formula here. And then this term here, which is the inner product of two matrices, now this is defined as the trace from x transpose times y. So this we will need quite a lot. And now there is just one super important thing I still need to show you. And this is the singular value decomposition. So, okay, big theorem, I know. But if you look at it, it's just easing you a lot of stuff. So what is the singular value decomposition? For every matrix X, which is n times p dimensional, there exist orthogonal matrices U and V and a diagonal matrix sigma, such that X is decomposed by the matrix product of U times sigma times V transposed. And the cool thing is that U, like the matrices here, the outer matrices are orthogonal, so they have an inverse and stuff like that. And that middle matrix is also interesting because it's a diagonal matrix. And the elements on this rectangular diagonal matrix sigma are ordered such that the largest is at the top left and then they all decrease. Just for notation, so the column vectors U, S and V, S are called left and right singular vectors, and the values of sigma on the diagonal are called singular values. We will need this. You can see this like a function, so SVD from X will return you here this decomposition, and this is also how you implement it or how you use it in Python, and then you can just work with this decomposition. As a matrix product, here's just a short visualization about the parts we have here. So X is equal to the matrix U is that here, and this is the matrix sigma, and this is the matrix V transposed. And now we have here the case that n, which is here this dimension, is larger than p, which is this dimension. And then you can see here that U is a square matrix and V as well, but sigma not, because it has to actually connect these two parts. And here we see that, yeah, the dimensionality n is larger than p, so we have here this rectangular format. And sigma only has elements which are non-zero on the diagonal, so this is here, and everything else has to be 0. And now if we compute U with sigma, then we see that actually this part here, all these columns here in U from P to N are multiplied with this part here, which is all 0. So that means that this part is actually not needed for the calculation, and sometimes this is also not mentioned. So there are different ways to mention or to denote a singular value decomposition. So you can have it like in this case here, where U is quadratic and V as well, but you can also truncate U here with by deleting this part, which is then anyways multiplied with 0. And yeah, similar thing happens if we have P larger to N. Here, this is P, and this is now larger than N, so this means that the rest here, the right part, is also 0, and this is multiplied here with V. So if we have here a 0 part, then we can also just delete it from the decomposition and nothing happens, so to speak. So one of the nice things about SVD is that it determines if a matrix is invertible, and it does so by the middle matrix sigma, because U and V are invertible anyways, because these are orthogonal, and if sigma is then invertible, the matrix is invertible if all singular values are larger than 0. This means in turn that the singular values also tell you if a matrix is invertible or not. And then we can actually compute that the inverse is given by a to the minus 1, which is V times sigma to the power of minus 1, the inverse of sigma, times U transposed. And as we already discussed, for diagonal matrices, yeah, the inverse is easily computed by just inverting all the elements on the diagonal. And then we can actually derive that what we stated is true, that the inverse is actually given here in this form. And we do this by checking A times the inverse of A, the supposedly inverse. And here we just insert the definition of the decomposition of A, which is given here top. And we multiply this here with the definition of the inverse we have given. And then we see that we have here V transpose times V, which is the identity matrix because V is orthogonal, and multiplying with the identity matrix doesn't do anything, so here we arrive at this term. And there we see now that sigma times sigma inverse is also the identity matrix, and then the remaining part is U times U transpose, and this is again the identity matrix because U is orthogonal. And then we can also do the same thing, only the other way around, and then we get this line here. And then let's close with a small trivia. So just have a look at this and try to answer it, and if you want, then you can look up the answer in the accompanying Mathy PDF. Okay, I hope you're now injected with all the important stuff of linear algebra. This was it. So everything you will see in the lecture from now on will be a repetition of the stuff we have learned today, or an application of the rules we have seen today. Or just something which basically builds on what have we seen today. And from now on it will be less technical and more application. So I'm happy to see you next time, and have a nice day. See you soon.